Hi, everybody. Happy Tuesday. We'll just wait a few more minutes for people to come in, then we'll get started. Go run to the bathroom, grab your coffee. Just another minute here. All right. Welcome, everyone. Thank you for joining us today for the next installment of our research speaker series. My name is Annika Trimble, and I'm the outreach coordinator for the Beaufort Delta region. If you're not familiar with the Aurora Research Institute, or ARI, we are the research division of Aurora College. So we have 3 branches in the Northwest Territories, and we support and conduct northern research in all kinds of fields. So these speaker series are just our way for connecting NWT residents with the research and discoveries that are taking place in our own backyards here in the territory. So on that note, I'd like to acknowledge that we in Inuvik are on the traditional land of the Gwich'in and Inuvialuit peoples, and we extend our deepest respect and appreciation for sharing this beautiful land with us. We further extend our respect to all First Nations, Inuit, and Métis peoples of the North who call this territory home. So before we get started, I'd like to go over a few housekeeping items so everyone's aware of how to participate in today's webinar. So you can submit questions to today's presenters using the Q&A function. So if you hold your mouse or hover over the bottom of your Zoom window, there's a control panel there and a Q&A button will appear. So that's the best place to put them. We don't follow the chat as closely, so just drop your questions in there and then we can make sure we get to everybody's and we don't miss any. Questions are only visible to the webinar, to the moderators or the facilitators here, and the presenters will answer them at the end of the presentation. So if anything happens, your internet goes out, your kids need you, you missed like that part you were just waiting for, don't worry, we're going to be recording this webinar. We're going to post the video on the ARI website, and we will put the link in the chat towards the end of the talk. So without further ado, I want to go ahead and introduce our presenters. We have Erica Hill and Kelty Ferguson joining us to talk about the impacts of erosion and permafrost thaw on the landscape and waters of Kugmallit Bay, which are very close to Tuktoyaktuk if you're not familiar with our local geography. So please take it away, Erica.
Hi, everyone. Thank you for taking time to join us. Today, we're going to be providing an update on the Beaufort Sea Coastal Restoration Project and a general overview of our preliminary findings. As Annika mentioned, there's going to be a Q&A session at the end. So if you have any follow-up questions or would like to have more detail on anything, please feel free to stay around, or you can feel free to access me by email at a later time. So I'm Erica Hill. I'm the principal investigator of the Beaufort Sea Coastal Restoration Project. I am also the Special Projects Coordinator at the Aurora Research Institute and a PhD candidate at Queen's University. My research typically focuses on climate change and permafrost thaw and their impacts on water runoff processes, hydrological processes, and water quality. However, I'm also interested in impacts on communities and northern infrastructure. Today, I'm going to be co-presenting with Kelty Ferguson, so I'll let her take a moment to introduce herself.
Hi, everyone. My name is Kelty Ferguson. I'm a GIS technician with the Aurora Research Institute. And then I'm also a RPAS or drone pilot with the Advanced Operations certification. So I do a lot of GIS, so that's digital mapping and cartography, focusing on kind of climate change and permafrost, but also with a big focus on education and outreach. So that's me.
So we hear a lot about how Arctic coastlines are rapidly eroding. However, it's important to realize that the rate of erosion varies with both space and time. Some areas are more vulnerable to erosion than others. And for most of the Arctic, the rate of erosion is increasing. Ugla and Twee from the Alfred Wegener Institute developed a map of historical coastal changes across the circumpolar Arctic. It essentially indicates what areas are more sensitive to coastal erosion. The regions in light yellow to orange represent areas with stable to slow rates of erosion, and the regions in red to maroon represent areas with moderate to rapid rates of erosion. From this map, we can see that the Beaufort Sea region is more vulnerable to coastal erosion as compared with other regions. They found that on average, the Beaufort Sea experienced an average erosion rate of 1.1 meters per year. And in some areas, particularly the Mackenzie Delta region of the Beaufort Sea, the average erosion rate was up to 10 meters per year. And this is only increasing. It's challenging to imagine the magnitude of erosion that's occurring, and it does manifest in a number of different ways. So here I've included some examples of the coastal erosion that we observed in the field in the Beaufort Delta region. In this study, we're more interested in the retrogressive thaw slumping, and you can see a pretty good example of a permafrost thaw slump that we found on Reindeer Island in the top right corner. So before we dive into a conversation about Arctic coastal erosion, I thought it might be a good idea to revisit the definition of climate change. When we talk about climate, we generally refer to parameters like temperature, precipitation, and wind. And when we talk about climate change, we talk about a change in the state of these parameters over an extended period, so typically decades or longer. On the right-hand side of the slide, I posted a map from Canada's Changing Climate Report produced by Environment and Climate Change Canada. The map is based on air temperature data that was collected between the years 1948 and 2016. Colors in yellow to dark maroon represent regions that are experiencing warming. So you can see that for all of Canada, we experienced warming over this period. However, the darker colors represent regions that experienced more warming. So it's clear from this map that Arctic regions are experiencing the effects of climate change in the context of air temperature at a more pronounced rate than the rest of Canada. And the Western Canadian Arctic in particular is experiencing climate change at a more pronounced rate than the Eastern Canadian Arctic. So why is this relevant to this presentation? Well, the climatic changes that we're observing in the Arctic are influencing other key environmental factors and accelerating the rates of erosion. So why are Arctic coasts so vulnerable to erosion? Well, they contain something called permafrost and ground ice. Permafrost refers to ground that remains at or below 0 degrees Celsius for at least 2 consecutive years. Permafrost is allowed to remain at this temperature in the Arctic because the climate in the Arctic is cold for most of the year, but also because there are a number of protective mechanisms, so vegetation and organic and mineral soil insulate the permafrost. Coastal permafrost is also protected by sea ice. Here are photos from the coastline of the Beaufort Sea that clearly show exposed ground ice. The top photo was taken from Tuktoyaktuk Island. The stability of Arctic coasts depends on the permafrost staying frozen, and this is threatened by climate change, which has led to increases in air, ground, and sea surface temperatures, rising sea levels, increases in the frequency of storm surge events, and decreases in sea ice duration and extent. The map on the right-hand side represents changes in sea ice extent over the past 40 years. The yellow line represents the median late summer sea ice extent in the Arctic for the years 1981 to 2010, whereas the white section represents the late summer sea ice extent that was observed in 2021. From this map, you can see that the late summer sea ice extent in 2021 was notably less than the historical median. This has significant implications for coastal permafrost. Wave action can expose coastal permafrost and ground ice. Sea ice offers protection to the coastline. However, decreases in sea ice extent make the coastline more vulnerable to other environmental changes, such as increases in the warmer air temperatures, warmer sea temperatures, and storm surges. As I mentioned earlier, the Beaufort Sea coastline is eroding at a faster rate than other regions. The Beaufort region is more sensitive to coastal erosion because of the nature of the permafrost and because of the nature of the ground material. Comparatively speaking, the permafrost in the Beaufort Sea region is more ice-rich, and the ground material itself is predominantly unconsolidated sediment, which can be easily eroded. In the Mackenzie Delta region of the Beaufort Sea, in addition to having ice-rich permafrost and easily eroded ground material, the landscape is populated by tens of thousands of small lakes and ponds. This makes these regions particularly sensitive to coastal erosion. During our mapping work, we observed locations where coastal erosion led to the catastrophic drainage of coastal lakes. By way of example, I just put up a couple pictures of one of our study sites in the Beaufort area, where you can clearly see a number of retrogressive thaw slumps that have initiated along the shoreline and are actually expanding backwards into one of the coastal lakes. Usually when a retrogressive thaw slump expands into a lake, you see catastrophic drainage of that lake into the bay. So coastal erosion is leading to unprecedented changes to the landscape. This is impacting communities, infrastructure, as well as ancestral sites. And I just want to take a moment to acknowledge a presentation by Michael Rourke, where he discussed the impacts of coastal erosion on ancestral sites. And you can actually access this talk via the YouTube link on the ARI website. One of the less discussed hazards of permafrost thaw and coastal erosion is water quality. Coastal erosion is delivering enormous amounts of sediment to the Beaufort Sea. And one of the questions we asked ourselves was, what does this mean for aquatic systems? In 2017, ARI was awarded $423,000 from the Coastal Restoration Fund to examine the effects of coastal erosion and permafrost thaw on Kugmallit Bay. This would involve detailed mapping and water quality studies, and a portion of this funding was also allotted to assessing the feasibility of using vegetation to mitigate the effects of permafrost thaw on the coastline of Kugmallit Bay. At the beginning of the project, we met with the Tuktoyaktuk Hunters and Trappers Committee to identify 3 to 4 study sites in the Kugmallit Bay area that were locally significant. For those of you that are not from the Beaufort Delta region, Kugmallit Bay is situated in the southern portion of the Beaufort Sea near the outlet of the Mackenzie River. We settled on Imnukpaluk, also known as Peninsula Point, Tuktoyaktuk Island, Gliptut area, and Reindeer Island. I would like to acknowledge Wayne Thrasher, who helped us with the Inuvialuktun names. So here are just some photos, aerial photos of our study sites. As I mentioned earlier in my presentation, we wanted to focus on places impacted by permafrost thaw slumping. So this is just give you a sense of the magnitude and nature of what we're dealing with. At this point, I'd like to hand over the presentation to Kelty, who will review the mapping component of the project.
Hi, let me just start my video. So as Erica said, I'll be talking a bit about the mapping. So what I will start with is our fieldwork process, and then I'll take a look at some of the data products that we've had and analysis of that data. So one of the primary parts of the project that I'm involved in is capturing pictures of the sites with drones. We're then able to use those pictures to create 3D models and maps of the site. And with that, we can track change over time. So first we have to get to the site. So we typically access these sites by either helicopter or boat. Along the way, we get to see some very beautiful landscape, such as the reindeer herd, which is always very exciting to see. And then once we're on site, we set up our kind of mobile field office with all our equipment and get to work. So we do fly the sites with multiple drones. The drone on the left-hand side of the screen is a fixed wing drone called the EB, and we use that primarily for our kind of big mapping. And then on the right, we've got a DJI quadcopter drone, and that we use to capture both photos and videos. So it's really flexible. We're able to capture small details, such as the vegetation plots that Erica had mentioned, which you can see in the center of this photo here. We can also do head wall and cliff edge surveys. We can capture oblique or angled photos of the landscape or of the entire site in one picture, as well as just documenting the fieldwork process, which is always fantastic to have. And I've just got a quick video here. You can see Erica and Ali from Parks Canada taking a look at the thermistor and vegetation plot, while we also swing over and look at the slump as a whole. Now back to that fixed wing drone, the EB, it only takes pictures looking straight down. But that is what we use for our mapping. And we do have multiple cameras that we can use in the drone. One captures RGB, or basically pictures like we see with our eyes. But then we can also capture thermal, or a heat map of the area, as well as multispectral, so different wavelengths of the site as well. So this is a picture of the flight path of that drone. So the pink line you can see is the path that the drone flew over the site. And the purple tiny rectangles you can see are each photo that the drone took. The larger purple square is the footprint of the photo, so the area that it actually captured on the ground. So once we've got all those photos and we're back in the office, we bring them into a processing software. So using the concept of photogrammetry and the fact that the photos overlap each other, we're able to then process the photos into 3D models. So it does that by extracting points that are shown in multiple pictures, and it builds the 3D model in space through that. And I will put a link to a model at the end of the presentation that you can explore. We also looked for other sources of data. So we went back to historic imagery, and there are aerial photos of the region from 1967. So you can see here that this is a photo that was taken out of a plane, so not a drone. So it's a little bit worse resolution, but still pretty clear and beautiful imagery, as you can see. And then by applying geographic location data to those photos, it's called georeferencing. We're able to turn those into data that we can use in mapping. So we took the 1967 photographs, as well as satellite imagery from 2004 from the Mackenzie Valley Air Photo Project. And taking those two data sets, we were able to go in and digitize the coastline. So that's basically creating a digital mapping feature of what the coastline was at those 2 points in time. From those data sets, I was able to buffer out the data, intersect the lines, basically perform some geographic analysis that created an output showing us the coastal change in the 54 years from 1967. Oh, sorry, that's 37 years from 1967 to 2004. And I'll also put a map or a link at the end of the presentation to this so that you can explore the data and zoom and look in. But basically what this map showed us was the 2004 coastline color-coded to show the amount of erosion or the amount of growth in the coastline. So the red to the pink is progressively where the land has eroded more. And then the green to the blue is where material has been deposited. So the edge of the coast has actually expanded from 1967 to 2004. And here is a zoomed in detail of an area that saw quite a bit of change. So you can see the red line, that is the 2004 coastline, where we are seeing about 150 to 200 meters of erosion over that time period. When we get into the hot pink, that is where we're seeing up to 400 meters of erosion. So this is one of those areas Erica was talking about where there was a lake that only had a tiny outlet to the bay, and now it is completely open to the bay. So I would say it's no longer a lake. We can also see on the right-hand corner where material has been deposited and there is now new land there, which I will show you in the next slide. So this is the 2004 imagery. You can see that lake has opened right up and there is quite a bit of new land over here as well. So now going back to the thaw slumps. So these are those sites where we're looking in particular detail with the drones. And we are looking at the head wall. So that is the active edge of the slump, which is the edge where it is retreating backwards as material thaws. So at these sites around Kugmallit Bay, we have done repeated drone surveys each year since 2018, as long as we were able to access the site and legally fly there. So this is the Gallop Tut area. The slump, it's a slump to the northeast of Tuck on the coast. And this is what it looked like in 2018. And with the repeated drone surveys, we can see the change over time. So these are the 4 years that we've carried out the drone survey at this site. Now, just looking at the images by themselves, it's a little tricky to see what has changed. So this is another place where we digitize those lines and superimpose them. So this background image is the 2021 past summer, how it looked, which is that dark maroon burgundy line here is the edge of the head wall. And then you can see on the map the previous year's head wall extents as well, all the way back to 1967. So you can see how the slump and the coastline has changed over time. And from this digitization, I was able to do further analysis with the digital shoreline analysis system, which is a tool created by the US Geological Survey, which has helped me to calculate the net change and various rates of change. So at the Gallop Tut site, we can see that at our kind of greatest net change in the 54 years from 1967 to 2021, we're seeing up to 100 meters of erosion, whereas we're also seeing some areas where there's been only up to 20 meters of erosion. So this is looking at the total change that's happened, but then I also want to take a look at the rate of change. So how much it's changing per year. So when we look at the entire timeline, it calculates out the kind of average rate of change as being 1 to 2 meters of erosion per year in some areas, and then kind of 0.5 meter of actual growth to 0.5 meter of erosion in other areas. However, I was then interested in taking a look at the more modern timeline as well. So I then carried out the regression rate on just the modern data set as well, the 4 years that we've done the drone surveys. And when I take a look at that, we can see some areas where it's just kind of the coast is eroding. We're seeing very similar rates of change. However, where the slump has formed, we're seeing up to 35 meters of erosion kind of per year. So that is telling us that these slumps are happening kind of at a much more sudden rate than the just coastal erosion that is happening everywhere. So just gonna quickly look at our other sites. This is Imnuk-Paluk. This is the 1967 imagery, and then I have superimposed the 2021 imagery on there as well. So this is a site kind of southwest of Tuk where we see quite a bit of change. Looking at that net change over the 54 years. This darkest color here is our greatest erosion, which is up to 400 meters of kind of retreat of the head wall. So quite a bit of change. And then we've also got Tuk Island, again, 1967 versus 2021. Not superimposed, but just kind of stuck on there. The whole island has not changed locations. And taking a look at the net change, we're seeing kind of an average of 80 to 120 meters of kind of coastal erosion or change over those 54 years. And then when I take a look at the rate of change, I did a quick comparison of the change over that whole period, and then a change over the more modern period of just 2004 to 2021. So you can see the color-coded rate of change for the whole period at the top. And then you can see how the rate of change has changed over the more modern period. So in some areas it has slowed, in some areas it has stayed the same, so retreating at a constant rate. And then in some areas it has increased. And this is where we saw a slump develop. So it makes sense that there was greater erosion at the area of the slump as well. So with that, I will turn it back over to Erica. I'm happy to answer any questions at the end, and I will link those two extra things for you guys to all take a look at.
Thank you. I'll just share my screen here. Okay. All right, so after the mapping component, the next component of the project looked at examining the effects of coastal erosion and permafrost thaw on water quality. So just revisiting permafrost thaw slumping. Permafrost thaw slumping is initiated when the vegetation and organic soil at the top of the permafrost is removed. This exposes the ice-rich permafrost beneath to the atmosphere, which initiates thaw and then eventually results in shoreline instability and collapse, particularly in areas where there are large amounts of ground ice. There have been a number of studies in the Peel Plateau region of the Northwest Territories that had looked at the impacts of retrogressive thaw slumping on water quality, particularly on landscape runoff and stream water. And they found that retrogressive thaw slumping leads to the mobilization and transport of particulate or fine material, such as organic material and mineral sediment, increases in major ions, and increases in the concentration of contaminants, in particular mercury, in landscape runoff. So what we wanted to do was look at what the impacts of retrogressive thaw slumping are on landscape runoff from thaw slumps at the coast. How we did this was we sampled landscape runoff that was flowing over thaw slumps, so over the disturbed terrain, and then we sampled landscape runoff that was flowing over the terrain next to the thaw slumps, so the undisturbed terrain. What we found was that landscape runoff from on the thaw slumps was notably higher in fine material, so organic material and mineral sediment, and major ions, much like what they had observed in the Peel Plateau region. However, we also saw that landscape runoff that was flowing over thaw slumps was notably higher in also trace metals, in particular aluminum, barium, iron, and manganese. In the absence of industrial and mining activities in the area, This is likely derived from permafrost thaw. So the question becomes, what implications does this thaw slumping and landscape runoff have for Kugmallit Bay and aquatic health? This became a challenging question to answer, largely because the water quality in Kugmallit Bay is heavily influenced by the sediment plume from the Mackenzie River. So in order to ascertain whether or not thaw slumping or landscape runoff from thaw slumping was having a persistent impact on water quality in Kugmallit Bay, we systematically monitored water quality from the mouth of the Mackenzie River up north along the coastline to north of our northernmost study site in the Beaufort area. And this sampling was carried out by Wayne Thrasher and Abraham Klingenberg from the Alluvial Land Administration. What we found was, as we expected, was the water quality of Kugmallit Bay was related to distance from the Mackenzie River outlet. So we saw that the concentration of sediment, organic carbon, major ions, and trace metals decreased with distance from the Mackenzie River. And we weren't really able to see a noticeable impact of thaw slumping on nearshore water quality. This doesn't mean that thaw slumping doesn't have an impact on water quality. It just doesn't have an observable, persistent impact based on our data. It could have an episodal impact, that is when you're seeing large slumping events or major rainfall events. So you might see some seasonal or spatial variability in this. However, we didn't notice it from our data set. Something interesting we did notice, however, is that in our graph, so on the bottom right of the slide, I've plotted the concentration of suspended trace metals, in particular aluminum, iron, barium, and manganese. And I've plotted that against distance from the Mackenzie River. What we're seeing is that the concentration of these suspended metals is decreasing with distance from the Mackenzie River, with the exception of a few isolated distinct points, where we see a little bit of an increase, or in some cases, a major increase in the concentration of suspended trace metals in Kugmallit Bay. The first is at a site that we called K7. And you'll notice from the graph on the left, or the figure on the left here, that K7 is adjacent to what looks like a site where a lake drained catastrophically. The next site is K5, and similar to K7, this site is also adjacent to a site that drained catastrophically. And again, the last one is K3, and this again is right next to a drained lake site. So although we weren't able to see a noticeable impact from our study sites, we do see an impact of lake drainage on water quality. And lake drainage is becoming an increasing risk as you see these thaw slumps expanding backwards into lake-rich terrain. And this makes me think that lake drainage is a big part of the question of how permafrost thaw and coastal erosion is going to impact aquatic health. So the last component of the project looked at assessing the feasibility of using vegetation to mitigate the effects of permafrost thaw on the coastline of Kugmallit Bay. So why vegetation? Well, as opposed to other forms of restoration or restoration materials, vegetation is natural. So if it doesn't work and it's eroded into the ocean, there's far less risk of pollution. Also, vegetation and organic material insulates the permafrost. It plays a very important role in keeping the permafrost cold. When a thaw slump is initiated, it removes vegetation and organic material from the ground surface. As a result, the ground within thaw slumps is typically warmer than undisturbed terrain. And this is why thaw slumps continue to expand, or if they're stabilized, they are reinitiated. So this initiated the question, can vegetation be used to restore the permafrost? Can we reverse this process and cool the permafrost down? How we assessed this was through a series of manipulations. So we installed a suite of 3 plot types into each study site. One plot was 1 by 1 meter on undisturbed terrain, so outside of each thaw slump. 1 by 1 meter plot was installed within the thaw slump on the disturbed terrain, so bare soil. And then we installed another plot within the thaw slump. And within that plot, we transplanted what we call a vegetation mat. So we actually harvested disturbed sod from the base of the thaw slump that contained a thick organic layer and vegetation, and then moved it to within the test plot. And then within each test plot, we installed ground temperature sensors down to 1 meter. Now we had 3 of each plot type at each study site for a total of 9 plots. So this is an image of what we saw at one of our, at a suite of plots that we installed at the Tuktoyaktuk Island site. So we see ground temperature from September through to September for each plot type. The black line represents the undisturbed plot. So that's the plot that we had outside of the slump where the vegetation and the soil layer hadn't been removed. And what we can see from this line is that it never increases to above 0, not even in the summer months. So this suggests that we have permafrost at 1 meter below the surface at this site. The red line represents the plot that was installed within the slump where we had bare soil. What we can see is that within the slump at 1 meter, we don't have permafrost. So the temperature increases to above 0 degrees Celsius in the summer. Now the blue line represents the plot where we transplanted a vegetation mat to within it. And the yellow line is a vegetation island. So in some cases in thaw slumps, you'll find little islands of vegetation that haven't been disturbed by the major slumping event. And since we found one of those in Tuktoyaktuk Island, we decided to instrument that as well. And what we found was that although the temperature underneath the transplanted vegetation mat did increase to above 0 degrees Celsius, meaning that there was no permafrost underneath, it is still cooler than the disturbed plot, which suggests that we can use vegetation mats to cool down permafrost or cool down the ground. So just a summary of what we found, the ground temperature at 1 meter below the undisturbed terrain remained below 0 degrees Celsius year round. The disturbed terrain was notably warmer than the undisturbed terrain. And we found that vegetation mats actually did cool the disturbed terrain. And the same observations were made at all of our other plots at the and as well as the ones at the other study sites. So what does this mean? This suggests that vegetation mats could be an effective means of restoring disturbed permafrost terrain, but there are important considerations that we have to make. We would want to use local plant species and locally sourced organic material and mineral soil. However, harvesting mats is very labor intensive. So another option might be producing mats, and that is one we considered. However, it is cost prohibitive. So that's that's a special consideration. Also, vegetation mats do not protect the coastline from wave action. So you could consider selecting sites that aren't as exposed to wave action, such as sheltered harbors, avoiding open ocean, or you would need to supplement your restoration initiative with other protective measures, such as wave breaks. However, I would caution against using man-made materials because, as I mentioned earlier, if it doesn't work and it ends up breaking or eroding into the sea, then you could have a risk of pollution. So that brings me to the end of the presentation. With that, I'd like to thank our support from the Nunavut Land Administration, Wayne and Abraham, as well as our wildlife monitor, Noel Raymond, and our project partners, Dustin Whalen from Natural Resources Canada, Allison Cassidy from Parks Canada, ARI staff, particularly Lance Gray and Greg Elias, and of course the Coastal Restoration Fund and the Polar Continental Shelf Program for providing us with funding.
Wonderful. Thank you, Erica, and thank you, Kelty. If you like, Kelty, you could turn on your video again, and to our attendees, if you have any questions, now is the time to share them in the Q&A. And then as they come in, we'll just decide who wants to take on which question. While we're waiting for people to kind of think them through, type them out, is there anything else that either of you wanted to share with us?
Sure, I will put in the chat a link to the web map that I shared earlier of the coastal change from 1967 to 2004. And I will also share my screen to show that for future video playback. So that is a link to that web map that you can explore. And then oh, sorry, Annika.
No.
I'll also put a link to a model of a slump head wall as well in the chat.
So for those of you who had kind of laggy or glitchy video come through, or if the video and the audio were competing, just our limited bandwidth in the north, these are the links you want to explore. So one is very interactive. You can, well, they're both interactive, but one of them you can really kind of explore the coastline and see the different rates of erosion, and exploring the model is really cool. That lets you on your own desktop kind of take a look at that imagery and rotate it around and all of those things. So yeah. Okay, so well, Kelty has one more link to put in the chat. And in the meantime, I see we have a question. I'm not sure which presenter it's for, maybe for both of you. It asks, are you working closely with communities and First Nations governments to know where, when, and maybe how they managed these loss of terrain in the past? So I'm not sure. Whoever would like to answer that, you can come off mute. So again, are you working closely with communities and First Nation governments to know where, when, and maybe how they managed these losses of terrain in the past?
It's a very good question. We have been working closely with communities to set the priorities for the project and select our study sites. And of course, community members have assisted with all of our fieldwork and data collection. And we do pretty extensive community consultations after our field seasons and as preliminary results come in. But that actually hasn't been part of our discussion, but it is an interesting point and it would be worth exploring.
Okay, and there was a follow-up that, yes, of course, the Inuvialuit or Inuit governments as well, obviously. So, okay, Kelty, did you have anything to add on that one, or?
No, so that second link was the model of the head wall. So that is something we've flown with the drone, and then built that 3D model so you can explore it on your own time.
And any other questions from the audience? Oh, we got one. Yes, please, by all means, submit them. If you've got more than one, you're very welcome. And for what it's worth, both of you guys, like, your imagery is so beautiful right now. It's been so cold for weeks here in Inuvik, and to see like the coastal imagery and that bright sun, and you could just feel the wind. And then Kelty, your representation of your data on the maps is very engaging. So like, really well done. On a personal note, it's just a beautiful way to communicate, like distilling what we're seeing on the ground into data is always a bit of a challenge, but to do it visually in the maps is, yeah, you guys have done really well with that. So we have one question. I think this is for Kelty. It's a very basic question. How long are those drone imagery flights? Like, how long do the flights last?
Yeah, that's not a basic question. It's a good question. So it depends on the size of the site. Most of these slumps that we're flying are on kind of the larger end, I would say, of some of our areas of interest. So typically each flight would take maybe 45 minutes to an hour per flight. And then we do fly each site 3 times with that fixed wing drone with the 3 different cameras. And then we also do additional flights when we can with that DJI quadcopter, just to kind of capture those extra bits of data or do the head wall survey if that's something we're interested in. So each time we're out at a site, and that's not even touching on setting up the ground control points to help us make our data more precise geographically and placing it in the correct location. Each site, I would say, takes about 5 hours to fully cover with the drone.
Okay, and the follow-up question to that is there a video of how you do it? Because it's super cool. Yeah, so that's another Kelty question.
No, not yet. We try to always capture some photos and videos of the process, but we haven't done a full dedicated drone video yet. So that's something to think about. Yeah.
There is, I'll just pipe it in, and like with my 2 cents, there is a video that was produced in partnership with a few other organizations about using drones in research. So from a broader perspective, there's something that kind of rings towards that. But yeah, I'm not sure. Anyway, so yeah, absolutely. It's really exciting to be able to get out in the field and assist with those projects and see them in action. One question, I think, for either of you, do you know or maybe have any ideas on why the terrain is gaining over the sea close to Tuck? So there's some places where things are eroding and other places where the shoreline seems to be building. So is it because of something natural or because of something the inhabitants are doing? Or is there a specific reason independent from that?
Well, I can try and touch on that a little bit. So some of the change that we would see in the map when it's just kind of in the matter of meters could just depend on the data quality. So we have those aerial photos from 1967 and then the satellite imagery from 2004. And if there's anywhere where the data isn't perfectly lined up, we'll see some variation. And the same in the local conditions at the time. So if there was a strong wind coming in over the land, the water might appear higher versus lower at a certain time. But then primarily where I saw areas where the land was growing was in these kind of very shallow sandbanky areas where just enough material, I guess, has flown out of the Mackenzie and been deposited on the shore enough that at the time that the photos were taken, we're seeing more land there than there had been before. But it's quite interesting to look at on the map and see where areas are losing a little bit of land or losing a lot of land or growing a little bit of land as well.
Awesome. Yeah. So sediment being taken away, but also being deposited in certain areas. So that's good. One more question. Oh, we've got a couple more coming in. This is great. We've got a little dialogue happening. This is what we love and what we miss so much from the live events. Next question. Do we have enough data to know whether the heavy metal contaminants are being found are coming from permafrost or are in the lake water?
I can't say without a shadow of a doubt, but I don't suspect that it's coming from the lake water. I think it's probably being delivered from the lake bottom sediments. So the lake bottom is usually like material goes into the lake and then deposits to the bottom. And so you usually have large amounts of material or soil material sequestered at the bottom of lakes. And so then when you have a catastrophic drainage event, much like a retrogressive thaw slumping event, all of that material is just dumped into the ocean. And the material that we were seeing, or the metals that we were seeing, the aluminum, barium, iron, and manganese, are all minerals that are usually derived from like mineral soil and permafrost. So I would suspect it's coming from permafrost and from the lake bottom sediments.
And are any of those metals metals of concern, like the way we hear about mercury, or are they just like naturally occurring and not really a concern?
They are naturally occurring, and they'd only be of a concern in specific concentrations. So I think understanding how it's integrated into the aquatic network is really a critical question, but it's also a super complicated one because, yeah, it's really about knowing where that goes and what ends up. But what I found interesting is that it seems as if the impacts of these lake drainage events on water quality are persistent. Like you're still seeing impacts on water quality even after the lake drainage event has occurred, which is something we didn't see with thaw slumping.
Awesome. Okay, thank you. So there is one final question. I'm going to put out, this is our final call. If we don't get any more, we'll just count this as our last one. So type away if you're feeling shy so far. This is your kind of your last chance. So one, maybe another one after this, but we have a question in the queue that says you used or perhaps did you use geological maps, for example, quaternary geology studies for slump observation? Did you use geological maps such as quaternary geological studies for slump observation?
I can answer that. No, I did not. So for those slumps, I looked at the imagery as I referenced in the presentation from 1967. So those nice aerial photos, and then the 2004 satellite imagery. And then after that, we have just looked at our own created by our partners drone imagery, or that ArtPass imagery. So no, but that is another data source that I could potentially consider.
Okay, I think that's it. We didn't have any other questions come in, so we're going to wrap that up there. We want to get you guys, honor you guys' 2 to 3 p.m. kind of commitment, but I just want to thank you both very much, Erica and Kelty. And we, of course, want to thank everyone else for attending the webinar today. We appreciate your time, your questions, your engagement. You can reach out to Kelty and Erica. They're both ARI employees, so you can find them and more about their work on our webpage. And as we spoke about in the beginning, a recording of this webinar is going to be posted on the ARI website in the next few days. So the link is in the chat, and you can follow us on Facebook for the announcement of the next virtual speaker series. Thanks, everyone, and we'll see you soon. Bye.